Hypergeometric distributions. In our first example, jury selection, a civil court jury of 6 members is being chosen from a pool of 8 men and 10 women. In part A, we're going to determine the probability distribution for the number of women selected from a pool of 8 men and 10 women. So the overall formula is here, probability of X, and that translates into the calculations in the table. So you can see when we have no women selected, that R becomes 0. And we're choosing from 10. So placing our values, A is 10, R is 0, and then X minus X becomes 8, and R minus X becomes 6. So that's 0 women, 10 men, all over the total, choose 6. And the numbers subtly change as we move up. The more women we have, this number increases all the way up to the total that we're trying to get, which is 6. And the number of men decreases from 6 down to 0. So that is the probability distribution in chart form. And then in graphical form, that is the number of women and the probability thereof, starting from 0 all the way up to 6. And you can see that it peaks around 3. And then we move to part B, which is what is the expected number of women on the jury. And for this, we use our short form of the expected value. So in this case, R equals 6, A equals 10, and our total number is 18. So plug in those numbers in. 6 times 10 divided by 18 is 3.33. Repeat. In our second example, red candies, a box contains 7 yellow, 3 green, 5 purple, and 6 red candies jumbled together. So that's 7, 3, 5, and 6 for a total of 21 candies. In part A, what is the expected number of red candies among 5 candies poured from the box? So we have our total, N, which is 21, R equals 5, A equals 6. Using our short form expected value, which is RA over N, 5 times 6 over 21, which is approximately 1.4285. So 1.5 candies, so between 1 and 2 in practical terms. So now we're going to verify that the expectation formula for the hypergeometric distribution gives the same result as the general formula of any probability distribution. So here the formula is a summation. So the expectation of X is the sum of each of the individual probabilities. So this is going to be no red candies. So that's 6 choose 0 times 15 choose 5, all over 21 choose 5. So where do these values come from? So 6 is the number of red candies, and that means of the remaining candies we have 15. So we're trying to figure out the expectation of simply red candies. So 0 red candies plus the probability of 1 red candy. So now we're at 6 choose 1 times 15 choose 4, all over 21 choose 5. And you're going to continue on down until you get 5 of the candies. So that's 6 choose 5 times 15 choose 0, 21 choose 5. And that, once you do the math, is exactly the same value. My last example, the wildlife management. In the spring, the Ministry of the Environment caught and tagged 500 raccoons in a wilderness area. The raccoons were released after being vaccinated against rabies. To estimate the population in the area, the ministry caught 40 raccoons during the summer. Of these, 15 had tags. So in part A, determine whether the situation can be modeled with a hypergeometric distribution. Well, the answer to that is yes, because raccoons are individuals, so they're separate entities. They may look all the same, but they're different people. And they can be tagged or not. So it's either success or failure, or yes or no, however you want to deal with that particular concept. So now let's estimate the raccoon population in the wilderness area. So our formula, our general formula, is RA over N. Well, we expect 15. We have 40, and we have 500. 40 raccoons. They caught 500 of them. We want to know how many there are in the total population based on our sample size. So now some quick math. We can actually exchange these two values. So we put N over here, and then it's 40 times 500 divided by 15. And then N, the number of the population approximately, will turn out to be 133,333, repeat. So approximately 1334. Thanks for listening.